When encountering a situation where 600 MCM conductors need to be connected to a switchboard designed for 500 MCM conductors, several solutions can be considered. Firstly, redesigning the system is an option. This involves consulting with the design engineer to revise the plans, switching to 500 MCM conductors. Another possibility is to update the existing switchboard or install a new one that can accommodate the 600 MCM conductors. Secondly, consider using a copper bus extension. This involves installing a copper bus extension from the switchboard to a new disconnect switch or breaker. Install the 600 MCM conductors in the existing conduits to the bus extension. From the bus extension, connect 500 MCM conductors to the switchboard. Thirdly, explore the use of a subpanel with a feeder tap box. Install a 500 MCM subpanel near the switchboard. Connect the 600 MCM conductors to the subpanel. Install a feeder tap box on the switchboard and connect a feeder whip from the subpanel to the tap box. Fourthly, investigate a custom-engineered lug kit. Consult with a manufacturer or electrical contractor who specializes in custom-engineered solutions. Determine if it is possible to create a lug kit that can accommodate the 600 MCM conductors on the existing switchboard. Fifthly, paralleling conductors in existing conduits is another possibility. Run 3 parallel sets of 4 500 MCM conductors in each conduit. This will provide the necessary ampacity and allow for the connection of 4 wires per phase on the switchboard. However, this option requires a larger wire size than originally intended. In more detail, let's consider the redesign of the system. This is typically the most straightforward, but potentially costly solution. The goal is to eliminate the need for adapting the 600 MCM conductors to the 500 MCM rated equipment. This may involve a comprehensive review of the entire electrical system design. The design engineer will need to reassess the load calculations to determine if 500 MCM conductors can adequately handle the anticipated current. If the load calculations permit, the plans can be revised to specify 500 MCM conductors for the entire run. This eliminates the immediate problem of mismatched conductor sizes. However, it could introduce other challenges. For example, the smaller conductor size might require adjustments to overcurrent protection devices. The existing switchboard might not be suitable for the revised conductor size, necessitating an upgrade or replacement. When considering switchboard replacement, factors such as lead time, cost, and downtime must be carefully evaluated. A new switchboard needs to be specified, ordered, and installed. This process can be time-consuming and disruptive to operations. Therefore, a thorough cost-benefit analysis should be conducted before opting for this solution. Next is using a copper bus extension. This approach provides a transition point between the larger 600 MCM conductors and the smaller 500 MCM switchboard connections. It involves installing a copper bus extension, essentially a conductive bar, that acts as an intermediary. The 600 MCM conductors are connected to one end of the bus extension. The other end of the bus extension is then connected to the switchboard using 500 MCM conductors. This method requires careful consideration of the bus extension's ampacity rating. The bus extension must be capable of handling the full load current without overheating. The connections between the conductors and the bus extension must be properly made to ensure a low resistance, high integrity connection. Factors such as connection torque, surface preparation, and the use of appropriate hardware are critical. Furthermore, the bus extension needs to be properly supported and insulated to prevent accidental contact and short circuits. Adequate clearance must be maintained around the bus extension to comply with electrical codes and safety standards. The third option is using a subpanel with a feeder tap box. This approach involves installing a 500 MCM subpanel in close proximity to the switchboard. The 600 MCM conductors are terminated in this subpanel. A feeder tap box is installed on the switchboard. A feeder whip, consisting of appropriately sized conductors, is then run from the subpanel to the tap box. This method offers flexibility in terms of conductor sizing and routing. It allows for the use of smaller conductors for the final connection to the switchboard while still utilizing the largest 600 MCM conductors for the majority of the run. However, it also introduces additional equipment and connections. The sub-panel must be properly sized and rated for the intended load. The feeder tap box must be compatible with the switchboard and the feeder whip conductors. The connections between the sub-panel, the feeder tap box, and the feeder whip conductors must be carefully made to ensure reliable operation. This solution may require additional space and coordination to accommodate the new equipment. Fourthly, a custom-engineered lug kit can provide a solution. This involves working with a manufacturer or electrical contractor who specializes in custom-engineered solutions. The goal is to design and fabricate a lug kit that can accommodate the 600 MCM conductors and the existing switchboard. This approach requires careful consideration of the switchboard's existing lug configuration. The custom lug kit must be compatible with the switchboard's mounting points and connection hardware. The lug kit must be able to securely and reliably connect the 600 MCM conductors to the switchboard. Factors such as conductor size, material compatibility, and torque requirements must be taken into account. The custom lug kit must be designed and tested to meet applicable safety standards. This solution can be costly and time-consuming, as it involves custom design and fabrication. However, it may be the most practical option if other solutions are not feasible. Lastly, paralleling conductors in existing conduits offers a solution by running 3 parallel sets of 4 500 MCM conductors in each conduit. This approach provides the necessary ampacity and allows for the connection of 4 wires per phase in the switchboard. Although this option requires a larger wire size than originally intended, this involves running multiple conductors in parallel to increase the overall ampacity. In this case, 3 sets of 4 500 MCM conductors are run in each conduit. This provides the necessary ampacity to handle the load while allowing for the connection of 4 wires per phase in the switchboard. This method requires careful consideration of conductor ampacity, conduit fill, and dirting factors. The ampacity of the parallel conductors must be sufficient to handle the load current. The conduit fill must comply with applicable electrical codes. Dirting factors must be applied to account for the increased heat generated by the parallel conductors. The parallel conductors must be properly sized and installed to ensure equal current sharing. This solution can be complex and require careful calculations and coordination. It may also require larger conduits to accommodate the increased number of conductors. Regardless of the solution chosen, it is important to consult with qualified design engineers and electrical contractors for proper approval and safety considerations. The electrical systems are complex and potentially hazardous. Any modifications or alterations must be performed by qualified professionals who are familiar with applicable codes and standards. The design engineer can provide guidance on the overall system design and ensure that the chosen solution is compatible with the existing electrical infrastructure. The electrical contractor can perform the installation work in a safe and professional manner. It is also important to obtain all necessary permits and approvals from local authorities before commencing any work. Electrical work must be performed in compliance with applicable codes and regulations to ensure the safety of personnel and property. Thoroughly investigate all options, compare costs and benefits, and make an informed decision. The key is to address the underlying problem of mismatched conductor sizes in a safe, reliable, and code-compliant manner. Here are some additional considerations when evaluating the various solutions. Firstly, cost is a major factor in any electrical project. Each solution has its own associated costs, including materials, labor, and equipment. The cost of redesigning the system can vary depending on the extent of the changes required. The cost of a copper bus extension depends on the size and complexity of the extension. The cost of a sub-panel with a feeder tap box depends on the size and rating of the sub-panel. The cost of a custom-engineered lug kit depends on the complexity of the design and fabrication. The cost of paralleling conductors depends on the number of conductors required and the labor involved. Secondly, downtime is another important consideration. Any modifications to the electrical system will require some amount of downtime. The downtime associated with redesigning the system can vary depending on the extent of the changes required. The downtime associated with a copper bus extension depends on the complexity of the installation. The downtime associated with the sub-panel with a feeder tap box depends on the size and rating of the sub-panel. The downtime associated with a custom-engineered lug kit depends on the complexity of the design and fabrication. The downtime associated with paralleling conductors depends on the number of conductors required and the labor involved. Thirdly, safety is paramount. Any electrical work must be performed in a safe and professional manner. The safety risks associated with each solution should be carefully evaluated. The safety risks associated with redesigning the system depend on the extent of the changes required. The safety risks associated with a copper bus extension depend on the complexity of the installation. The safety risks associated with a sub-panel with a feeder tap box depend on the size and rating of the sub-panel. The safety risks associated with a custom-engineered lug kit depend on the complexity of the design and fabrication. The safety risks associated with paralleling conductors depend on the number of conductors required and the labor involved. Consider the implications of each solution on the long-term reliability and maintainability of the electrical system. A well-designed and properly installed solution should provide years of trouble-free operation. A poorly designed or improperly installed solution can lead to frequent maintenance issues and potential failures. The chosen solution should be compatible with the existing electrical infrastructure and should not introduce any new points of failure. It should also be easy to inspect and maintain. The electrical system should be designed to be easily accessible for maintenance and repairs. The chosen solution should not create any hidden or difficult-to-reach connections. Consider the impact of each solution on the overall efficiency of the electrical system. Some solutions may be more energy efficient than others. For example, using a copper bus extension can minimize voltage drop and improve energy efficiency. Paralleling conductors can also reduce voltage drop and improve energy efficiency. When selecting a solution, consider the long-term energy costs associated with each option. Select a solution that is both cost-effective and energy efficient. The NEC, or National Electrical Code, provides comprehensive guidelines for electrical installations. This code is updated every 3 years to reflect the latest industry practices and safety standards. It is essential to comply with the NEC when designing and installing electrical systems. The NEC covers a wide range of topics including conductor sizing, overcurrent protection, grounding, and wiring methods. The NEC also provides specific requirements for switchboards, panel boards, and other electrical equipment. Ensure that the chosen solution complies with all applicable NEC requirements. Here are some relevant NEC articles that may be applicable to this situation. NEC Article 240 covers overcurrent protection. This article provides requirements for the selection and coordination of overcurrent protection devices, such as fuses and circuit breakers. NEC Article 310 covers conductors for general wiring. This article provides requirements for conductor sizing, ampacity, and installation. NEC Article 310.15 provides tables for determining the allowable ampacity of conductors. These tables take into account factors such as conductor size, insulation type, and ambient temperature. NEC Article 310.15b3 covers adjustment factors for ambient temperature. This section provides guidance on adjusting conductor ampacity for ambient temperatures that are higher or lower than the reference temperature. NEC Article 310.15b3 covers adjustment factors for the number of conductors in a raceway or cable. This section provides guidance on adjusting conductor ampacity when multiple conductors are installed in the same raceway or cable. NEC Article 366 covers auxiliary gutters. This article provides requirements for the installation and use of auxiliary gutters, which are used to supplement wiring spaces at switchboards, power boards, and other equipment. NEC Article 408 covers switchboards and panel boards. This article provides requirements for the construction, installation, and wiring of switchboards and panel boards. When selecting a solution, it is essential to consult with qualified professionals who are familiar with the NEC and other applicable codes and standards. These professionals can provide guidance on selecting the appropriate solution and ensuring that the installation complies with all applicable requirements. Additionally, document all decisions and calculations related to the chosen solution. This documentation will be helpful for future reference and for demonstrating compliance with applicable codes and standards. The documentation should include information such as load calculations, conductor sizing calculations, overcurrent protection device selection, and conduit fill calculations. In summary, several solutions can address the issue of connecting 600 MCM conductors to a switchboard designed for 500 MCM conductors. These solutions include redesigning the system using a copper bus extension, using a sub-panel with a feeder tap box, using a custom-engineered lug kit, and paralleling conductors in existing conduits. Each solution has its own advantages and disadvantages. The best solution will depend on the specific circumstances of the installation. Consult with qualified professionals and comply with all applicable codes and standards to ensure a safe and reliable electrical system. By carefully considering all of the factors involved, an informed decision can be made and the solution that meets the specific needs of the installation can be implemented. The most important thing is to ensure the safety and reliability of the electrical system. This requires careful planning, proper installation, and compliance with all applicable codes and standards.